Constraint programming, often called CP, is a powerful way to solve complex problems. It is a problem-solving paradigm from computer science and artificial intelligence. Think of it like a very clever puzzle solver. CP helps us arrange all the pieces correctly. It focuses on making choices that follow certain rules. Constraints are rules that must hold true. For example, you can't invite more people than your house can hold. Or two guests who don't get along shouldn't sit together. CP solvers use algorithms to find solutions. To understand constraint programming, we must first understand its basic building blocks: variables, domains, and constraints. Variables are the unknowns in our problem, representing the decisions we need to make or the values we need to find. Each variable has an associated domain, which is the set of all possible values that the variable can take. In a Sudoku puzzle, each empty cell is a variable with a domain of numbers 1 to 9. Constraints are the rules that define the relationships between variables. They restrict the combinations of values that variables can simultaneously take. The CP solver finds values for variables that satisfy all constraints. Constraint programming is crucial for solving optimization problems. In many real-world situations, we are not just looking for any solution, but the best possible solution. For example, a delivery company wants the shortest route to save time and fuel. This is where optimization comes in. CP can find solutions that are optimal according to some criteria, often called an objective function. To handle optimization, we add an objective function to our constraint problem. This function measures how good a solution is. For instance, in the delivery route problem, the objective function would be the total distance of the route. The goal would be to minimize this function. The CP solver searches for a valid solution that also gives the best value for the objective function. CP also plays a vital role in many areas of artificial intelligence, AI. Many classic AI problems can be framed as constraint satisfaction problems. Think about tasks like planning a sequence of actions for a robot or natural language understanding. These rules are essentially constraints. CP techniques are fundamental to building intelligent systems that can solve complex real-world tasks. Automated planning and scheduling systems heavily rely on constraint solving. CP allows AI agents to explore large search spaces efficiently, making it a cornerstone technology for practical AI. One of the most fundamental techniques in constraint programming is backtracking search. Backtracking is a general algorithm for finding solutions to computational problems, notably constraint satisfaction problems. It works by incrementally building candidates for the solutions and abandoning a candidate as soon as it determines that the candidate cannot possibly be completed to a valid solution. The process involves choosing an unassigned variable and trying to assign a value to it from its domain. After assigning a value, the system checks if this assignment violates any constraints. If the assignment is consistent with all constraints, the algorithm moves on to the next unassigned variable. This continues until all variables are assigned. If an assignment leads to a constraint violation, the algorithm backtracks. It undoes the most recent assignment and tries a different value for the variable. If all values for that variable have been tried and failed, it backtracks further. Backtracking systematically explores the search space of possible assignments. It can be visualized as exploring a tree of possibilities, while backtracking guarantees finding a solution. If one exists, it can be very slow for large problems. Enhancing efficiency: the role of constraint propagation. While backtracking search is a core method, it can be inefficient on its own. This is where constraint propagation comes in. It reduces the search space, making backtracking faster and more effective. By actively using constraints, values are removed from domains that can't be part of any solution. This early detection of inconsistencies helps prune large parts of the search tree. Constraint propagation and backtracking search work hand in hand. Smart searching, using heuristics to guide the way. Even with constraint propagation, solving complex constraint problems can take a long time. The search space can still be vast. This is where heuristics come into play. Heuristics are essentially rules of thumb or smart guesses. They help guide the search algorithm towards promising areas of the search space. They do not guarantee finding a solution faster, nor do they guarantee finding the optimal solution in optimization problems. However, in practice, Good heuristics can make a dramatic difference. In constraint programming, heuristics help the solver make sensible choices during the search process, particularly when backtracking. There are two main types of heuristics commonly used in constraint programming. The first is variable ordering heuristics. These heuristics decide which unassigned variable to select next for assignment. A common strategy is the fail-first principle, choosing the variable that is most constrained or has the smallest remaining domain. The second type is value ordering heuristics. Once a variable has been selected, these heuristics decide which value from its domain to try first. Crafting effective heuristics often requires some understanding of the problem's structure. Constraint programming in action real-world applications. Constraint programming is a practical tool used to solve a wide array of real-world problems across many different industries. One of the most common application areas is scheduling and timetabling. Consider the complex task of creating a university timetable. You have courses, lecturers, students, rooms, and time slots. Constraints include: a lecturer cannot teach 2 courses at once, a room cannot exceed its capacity, and students should not have clashing lectures. CP excels at finding feasible timetables. Another significant application is resource allocation. Businesses and organizations often have limited resources, such as budget, equipment, or personnel. They need to allocate these resources effectively to various tasks or projects. For example, an airline needs to assign aircraft and crew to flights. Constraints might involve maintenance schedules for aircraft, crew qualifications, and flight hour limitations. CP can help find an allocation that meets all requirements and perhaps optimizes a goal, like minimizing costs or maximizing resource utilization. Logistics and supply chain management also benefit greatly from constraint programming. Problems like vehicle routing, where companies need to plan efficient routes for delivery trucks, are classic CP applications. The advantages of employing constraint programming. One of the primary advantages of using constraint programming is its declarative modeling approach. When you use CP, you focus on describing the problem itself. You define the variables, their domains, and the constraints that govern their relationships. You do not need to worry about the low-level details of how the search for a solution will be conducted. This separation of problem statement from search strategy makes it easier to develop and maintain models for complex problems. It allows domain experts to express their knowledge naturally. Constraint programming is highly flexible and can handle a wide variety of complex constraints. These can include arithmetic constraints, logical constraints, and even global constraints. Global constraints are special constraints that capture common patterns involving many variables, such as ensuring all variables in a set take different values. Another significant benefit is the efficiency of CP solvers for many types of combinatorial problems. Modern CP solvers integrate powerful techniques like constraint propagation and sophisticated search heuristics. They can often find good solutions quickly, even for NP-hard problems. Moreover, CP solvers can not only find a single solution or an optimal solution, but can also find all solutions, or prove that no solution exists if the problem is unsatisfiable. Finally, constraint programming tools and libraries are becoming increasingly accessible. Gazing forward, the future potential of constraint programming. The field of constraint programming is dynamic and continues to evolve. Researchers are constantly working on developing more powerful and efficient CP solvers. This includes creating faster algorithms for constraint propagation and designing more intelligent search strategies. There is also ongoing work on new types of global constraints that can capture even more complex problem structures. These advancements aim to push the boundaries of what problems can be solved effectively using CP. A particularly exciting area of future development is the integration of constraint programming with other techniques, especially machine learning. Machine learning can be used to learn effective heuristics automatically from data. For example, an ML model could learn which variable or value ordering heuristic works best for a specific class of problems. Conversely, CP can be used to incorporate domain knowledge and constraints into machine learning models, making them more robust and interpretable. New application areas for constraint programming are continually emerging. As our world becomes more interconnected and complex, the need for sophisticated planning, scheduling, and resource allocation tools increases. CP is well suited to address challenges in areas like sustainable development, where resources must be managed carefully. The ability of CP to handle complex interdependencies makes it a valuable tool for these modern societal challenges. In conclusion, the future of constraint programming looks very bright. If you learned something new, like the video, share your thoughts in comment section, and don't forget to subscribe the channel for more related videos.